So this is also a way for us to learn about earthquake cycle. So how do we balance the co-seismic and inter-seismic of a fault system? So I'll show some just examples from San Andreas Fault, but you could imagine it's exactly like what would happen on Great Sumatran Fault or any more vertical strike slip fault. Then I'll show ideas of dislocations. What is this word? And then I'll show the example of this theory called strike slip parallel displacements from simple screw dislocation. Do a few examples, and then we'll do our exercise from Izmit earthquake, so from Turkey, because we have some data. Okay, so this just shows some different parts of the San Andreas fault system, and there was a big earthquake in 1906 called the San Francisco earthquake that was famous for kind of being at the beginning of modern seismology. You know, people started thinking about how earthquakes can work, and so, you know, they talk about elastic rebound and Harry Fielding Reed, the Reed model. This came from there. So, but here's an example from north. So this is up here, right here. And so even in 1906, there was some surveying, you know, with mostly they would use a theodolite. And so you measure the distance and the angle change, and then you can compute the displacement. So the vector scale you can see here is meters. So these stations, this one moved about 1 meter. But as you see, as you come close to the fault, it gets larger, right? Over like 10 kilometers, okay? And then once we cross the fault, so between 6 and 7 is the fault, and you see the direction changes, right? It's right lateral. And then as we go away from the fault, it goes down again. So this is co-seismic signal with the highest displacements at the fault. And so here's an example of some damage. And the famous picture of the surface rupture. So it's just tearing the ground, you know, and here, remember, I was talking about the effect of the vegetation holding the blocks together. And then this was this famous fence that they show that was offset. So the idea of this elastic rebound is, you know, you start at the beginning, and you, because of the plate tectonics, you slowly deform, and then in the earthquake, it snaps back, right? Now, one small misconception is that they show always the fence, and so here it's, you know, kind of looks like this, but the misconception is this bending occurs at about 10 kilometers. So it's like if it's a 10-kilometer long fence, you'll see it bend, but not across the field. So it's a small but incorrect way almost every one of these cartoons is drawn when they talk about elastic rebound. So these idea of dislocation is it's called a displacement discontinuity in a continuous body. So it comes from mineralogy. So if you think of crystal, like some salt or something, you know, you have you have the lattice, these blocks, you know, these blocks, and you may displace like one unit cell over, but you come down, and then at some point you get to the end, and there's no displacement. So you kind of make a circuit. You call this the displacement, and then you go around, you follow around, come to the other side, and you find it. So this is why this one's called a screw. It's like, you know, if you're screwing something into the wall. And so this kind of looks like a strike slip fault, maybe, you know, just going like this. And then this, so in this case, the slip is parallel to the tip. The direction's the same, the tip and the slip direction. So the other kind of dislocation is called an edge dislocation. Same idea, but in this case, the motion is perpendicular to the tip. So it's just like an edge. So this, the mathematics that goes with dislocations comes from the mineralogy people. So crystallographers, they develop this mathematics. So we can try to use it, and it's actually surprising because it works so well. So here's the basic idea. So this is important conceptualization for earthquakes and earthquake cycles. And really, the way I like to think of it is more the thick lithosphere model is the one that is more kind of consistent with how you think the Earth works. And so just look on the left here. But if you have a fault, so you can imagine the San Andreas fault, or you can imagine Great Sumatran fault. You can even do it with a subduction zone, but let's just keep it this way for now. And the two sides are moving horizontally. So we know at depth, usually this depth D, below some depth, it's stably sliding. So what is D? How deep is usually this transition, do you guys think, in the Earth? Usually, well, more 10 to 15. Because it's vertical, it might be 30 kilometers down dip on a gently dipping fault, but it's about, easy way to think is about 10 because of temperature. So like in California, it's about 30 degrees C per kilometer. So by the time you get to 10 kilometers deep, it's 300 C. So it's too hot for frictional processes to dominate. So instead, it's slowly just sliding. So you have, for geologists, this would be where we're making myelinites down there. And so we're steadily sliding, but above it's locked. So you just have frictional behavior. You have to load it up enough, load, and then snaps the earthquake. So what this guy Thatcher, the USGS scientist, he had this. It wasn't his idea, but he explained it very simply. Was that you could think of the behavior of a fault is kind of two stages, the co-seismic and inter-seismic. And so in a way, the inter-seismic is what's happening down here, steadily slipping. And so he shows this plot of, so basically y would be distance perpendicular to the fault. So y would on here goes like, is this direction right here, okay, y. And then x would be parallel to the fault. So what he's showing is the displacement parallel to the fault, how it changes as you approach the fault and go away from the fault. And so this steady motion at the far distances is the total displacement, delta U, over time. Let's say over 100 years, 10 meters, okay? But it happens steadily. But at the fault, it's stuck, especially right here. Nothing's happening, so strain's accumulating, and then it has to be released. Boom. And so, it goes like this, and then, and that snap is when this part D slips. And so that part is called the co-seismic part, and that's this one here. So same thing, distance from the fault is the Y, but then delta U is the co-seismic slip at the fault surface, and it decreases going away from the fault. So the important thing then is that if you can add, if you just look at this, you say, all right, well, if I add this much right here, and then I come this way, add a little bit there, a little bit there. When you add these two together, it's like block motion, right? So over the long term, it just goes along like this. But it has two stages. It's kind of like, it strains, snap, and then it's going to strain, snap, strain, snap, okay? So that's the, inter-seismic, co-seismic, inter-seismic, co-seismic, because the edges of the model is plate tectonics, just pulling things along. But this is kind of like, has this depth variation because of we think the fault has frictional behavior. So this is the cross section. So this would just be a slice, just right through here, just this face. And so what we see in co-seismic is just this part moves, and below it's stuck. And then inter-seismic, this part's always steadily moving below D. Okay? So we'll play with this because these equations are really simple, actually. So you can do it in Excel, and maybe it will be clearer. Because I see your faces, you're like, what? So hopefully but you have to ask questions because we have to do this together. So, but let me go through the story a little bit more and then we'll come back. But just to show the equation, this one says basically this is the change in displacement with time. So this is basically displacement rate is equal to the slip rate divided by pi times a tan of y over d. So this is just the equation for this curve. Okay? And so, and then this one is the strain rate, which is just basically the derivative of this. So the highest strain is at the fault, and it goes down. And the strain is anti-symmetric for co-seismic and inter-seismic. So when you add these two together, you also get no permanent strain. That's what I mean by, this strain is balanced with this one. And one important thing, and this is why I'm doing this partially for this class, is that the half width of the strain, or you can think of kind of the wavelength of this gradient and displacement, it's controlled by the depth. So the deeper the fault is, the wider the effect is. Or the shallower the fault, the narrow. And so this is something you always should keep in your mind, how sharp is the displacement field? If it's very sharp, it must be a shallow source. If it's really broad, it must be a deep source. And so this is a way to prove that. So I'll go through some more of the story and then we'll come back. Okay, so here, coming back, so this is, you guys who came in late, I started with this, but we're back to it. So here you can see this was one earthquake. So it happened in like a few seconds. This side went this way, this went that way. But you can see, look at the magnitudes are larger close to the fault and they get less going this way. Same with here, opposite direction, but decreasing away from the fault. So what I did then here, I should maybe show this in multiple pieces, but this plot shows the UX displacements versus distance, perpendicular to the fault. So this is 0, and this says 10 to the 4th meters, so minus 10 kilometers, and then this would be 10 and 15. And so here the X's show the arrow length, okay? So like negative 1.5 or negative 2, that one is this one right here, okay? So if you take 7, you put it over here, like about just a little bit more than 2, right? So then if you look at, let's say 12, you see it's maybe closer to 1. So that's this one, or this one of these guys. So in general, as we go away from the fault, if you just look at the black, they get smaller, okay? And then on the other side of the fault, you see up here almost 2.5 going down to 1.5. So that's these guys here, 6 and 5 going to there, okay? So we see this asymmetric co-seismic signal, just like Thatcher showed. It's just this one right here. Okay? Yes? So what I did was I just used what we're going to do in our exercise, and I just changed the locking depth. I just said, all right, well, how deep was the rupture? So I just calculated each time D, 1 kilometer, 2 kilometer, 3 kilometer, 4 kilometer, 5 kilometer, 6 kilometer, 7, and I was comparing with the observations. And so what you can see, so this very tight one is a shallow one. That's just 1 kilometer deep. So D is very short. So remember what I said, that displacements change fast when the source is shallow. And as I pull the bottom down, the displacement field becomes more smooth. So you can see this is 1 kilometer deep, 2 kilometer, 3 kilometer, 4 kilometer, 5 kilometer, 6 kilometer, 7. Oh, we're just about going through the data. And then 8, 9, 10, 11, 12, 13, 14, 15, 16. So I show that the best, so when you're out at about 15 kilometers deep, it's too wide. It doesn't drop off as fast. And so this is just a quantification of that. So root mean square error, it's just a misfit between these calculated values and the observed ones. And so the misfit goes to some minimum and then gets worse again. So that's how I know the best fit is at 7 kilometers. So this is a kind of valuable way of interpreting geodetic data. And it's exactly what people do with more sophisticated. You may hear, inverse model to fit dislocations, INSAR, something like that. It's the exact same idea, but just three-dimensional, more complex calculation. Okay, let's try this one. So this is the basic earthquake cycle in one dimension. So so this is a little bit of a different analogy, but if you have you can think of plate tectonics as, I'm pulling, my arm is plate tectonics, okay? But there's a spring and there's friction, right? And so I pull, and then I overcome the strength of the bottom of this thing, and that's an earthquake. And so then, let's do another one. Okay? So this is like one-dimensional earthquake cycle. But so if you just say, well, let's take that block and let's flip it on its side, for our model, then we're just pulling from the side, and it gets, it's like this, it gets stuck, and then it snaps, and then I do it again, snap, snap. So this is, this is simpler than what I'm showing, but it's the beginning. So let's look at another example, especially because we have our team here, the tsunami team. So this is another way we can think about earthquake cycle in subduction zones. So this is my second lecture. If we get to it, I can show. So let's watch. So this doesn't quite show as well, but because, let's see if it's going to show there. Okay, so watch what happens. So this is stuck. And there. So you can see this, it's dragging the other side. Now underneath here, it can still be sliding steadily. Okay, so it's really dragging it, it's stuck. But so on this side, it's steadily creeping. So then watch what's going to happen. Ready? And then the other important thing is you see, because it's stuck, it's actually taking that GPS receiver and moving it. Opposite of how you would think it should move because of the faulting, right? Like, the top should be going this way and the bottom should be going like that. But because it's stuck, it's actually communicating the stress across the fault to the other side. So let's try. So ready? Uh-oh, you guys. I'm nervous. Okay. Okay, so right there you see what happened is that's that elastic rebound. So we pushed it down and then it snaps back. But the snap is close. It's only just right in the neighborhood here, and it displaces the GPS back. So it's analogous to what I've been showing for the strike slip case, but instead of being, this like parallel like this and dragging across the fault, it's going down and dragging and then snapping. So same concept. So this is critical. So it's good that you guys are asking because, okay, and then here, because the seafloor was lifted, it sends the tsunami, right? And so the double problem of the tsunami-genic systems is the shaking and the tsunami. So let's just watch it one more time. And I want you to really think of, okay, this is inter-seismic, period. So plates are locked, stress builds along the contact, but the surrounding volume deforms. And the example is the GPS receiver, but also the ground is lifting, right? So this is the case, you know how sometimes the corals they die, right, in between the earthquakes. And then now, So at that instant, if you had lifted a coral out for 100 years, it would be submerged again. And we lift the seafloor out in here, producing tsunami. So, but the key thing is it's this two-stage model. So inter-seismic, co-seismic. Okay. So this is a little bit more complicated, but this is actually what was observed in the Japanese earthquake from GPS, from the GPS network. So maybe you guys have seen this already. But this shows, so this is GPS from GSI. So left is horizontal, right is vertical. So the vertical is always noisier in GPS. Let's watch, because this shows, what this will show is mostly co-seismic, because it's just that day of the earthquake. So nothing's happening. There's the main shock, and you see it's pulling, and this actually sends the dynamic, it sends the surface waves. But in our case, we're not worrying about the dynamic parts of the problem, we're just worried about the static part, which is these arrows once the waves go through. And so what you can see here is watch it one more time, and then I'll interpret it. So this is complex because it has dynamic parts, but the main shock with big waves moving through Japan. And then there's an aftershock, right, about now. Okay, so this key language, I say static and dynamic. So dynamic means the waves move through. It's time dependent. But static is the final, total, time independent change. And that's what these arrows show. So here, this is a 3D problem now. So here's another example of the deep, this is inter-seismic for another part of the San Andreas Fault. So remember in my video at the beginning of the lecture, I just showed all these arrows. This is what's measured every day right now by continuous GPS. So if you just take the points in this box and you measure their length, okay, and then I plotted them over here. So this is velocity versus distance in North 40 West. So it's basically this length. And I just said 0 at the San Andreas Fault, but I could have said 0 here. But the important point is that the arrows, they don't change shape steadily. They actually change shape kind of right on top of the fault a little bit faster. And so I took these data and I did this factor style calculation, and I just said, well, what, if I assume that depth is 12, which is what the seismicity is for California, 12 kilometers, then I say, well, what slip rate at depth will fit those data? And so you can see 30 millimeters a year to 37 basically balance the data pretty well. In this case, yeah, I'm assuming because it's such a simple model, I'm kind of only having one free parameter. So in the last case for the co-seismic in San Francisco, I knew the slip on the fault, which was like 4 meters total because it's 2.5 and 1.5. And so I was looking at D. But in this case, I said, well, I know D because of seismicity in the fault region. I know it's about 12 kilometers. But what I really want to do is figure out what the rate is, what the U dot in his equation, or just the deep slip rate is. So then I just tried different numbers, and 30. So what you can see is if this were too low, if this was 20, this thing would really miss the data. So it has to be 30 to 37. So it's simple calculations. So you may say, what I'm doing is maybe it's complex or it's too simple. But actually, we wrote a paper using just this simple math. So it's usable in very basic sense. And then you can get much more sophisticated. So what I've showed you then, this example is co-seismic. this example is inter-seismic, okay? So the last example is more complicated, which is up, dip, change in slip. So here was the problem. Here's a study site we worked on in California, San Andreas Fault here. So, and we mapped the fault, and we dug these trenches. Okay, so we can discuss trenching in a few days, but the basic idea was, all right, we need to know where the fault is, so we cut these trenches. Those are called fault locators, and then you cut fault parallel because we wanted to find something that crossed the fault and was offset. So my student, Jerry Young, she did this work, and we found down in this area a gravel, it's the edge of a gravel that was offset. And this is what it looked like. So now you see the scale, just 10 meters. So this is just right in here, this little area here. There, let's see, 1, 2, 3 trenches. 1, 2, and 3. So these 3 bigger trenches are these 3. And then we dug with the shovel many times, just cutting back. And so we found, so this gray shows this sheet of gravel. So it was gravel coming in to the fault and across the fault, and then it was offset in the earthquake. And so we mapped, the dots are where it's natural edge of the gravel, and the crosses are where it was faulted. And so it clearly comes in, hits the fault, broken, leaves the fault unbroken. So 3 meters of offset right at the fault, okay? But what we found was that at some distance, about 1,000 meters away from the fault, somebody measured, about almost 20 meters of offset between these 2 stations. So we thought, well, how do you reconcile this? How do you reconcile 3 meters at the surface, but then the edges are, moved, the monuments are moved more like 20. So we used multiple dislocations. We used one that went to the surface. We just did 3 meters right here. And then I said, well, how deep do I need to pull this transition zone from 3 to 20 down to fit the data best? And so what I could do is show that at about 250 meters, somewhere between, let's say, 50 to 250, it changed from 3 to 20 meters. So it just means that, at depth, it had lots of slip, and then as we come up to the surface, the slip must have been distributed or it died. And so this approach, which is just using these dislocations, let me kind of explore that transition. So this is a more complicated case where it's not uniform over the fault surface, but same style of study. So that's my example of 2D dislocations for strike slip. So this new lecture, but same exact kind of outline, except that it's dip slip. And so motivations from normal and blind thrust faulting, basic ideas of dislocations, and then dip slip from a simple edge dislocation model. So I showed you already Bora Peak earlier this morning. We saw this already. And then I said, well, this is what was observed in the earthquake itself. So, how can we model that, or how can we understand it? So I'll show you in a moment. The other thing that happened was in 1989 was an earthquake in southern Bay Area. There was a blind thrust fault. So it didn't break the surface. It was just slipping at depth. So it looks like this. It was oblique slip, but in part of it was just dip slip. We can just take the dip slip component. So it just cracked the ground, but it didn't really break. It looks like it was about 2 or 3 kilometers to the top. And so here's the seismicity here. Main shock was there and it went up dip. Damage in San Francisco. So this is a model using a fully 3D dislocation. So this would be what we could do tomorrow afternoon with Coulomb. And what this shows is the contours show vertical, so how much it went up, and then this is 1989, so GPS is just being used at this time for the first time. And so this shows the dislocation, or the horizontal motion. So you see it's pulled in and pushed out, pulled in and pushed out. So this is showing the 3D effect of this finite rupture that's only this length here. But it also shows a little bit of the pattern from the San Francisco earthquake, where the largest displacements are fairly close to the fault, and as you get further away, they go down. But it has that same decay away from the fault. It's just kind of a short earthquake. It was only 7.3, not 7.9, so it's not stretched out as much as the 1906 earthquake. So how do we analyze this? Same idea, edge dislocation, screw dislocation, but now we use edges. And this, we can go into the detail in a bit more. But basically, what we can do is we can use the same idea as Thatcher showed, where you just have a single discontinuity that goes to minus infinity, but in this case, it's edge dislocation going up instead of the screw dislocation going horizontal. But one of the really powerful parts of the dislocations is that we can make it, because it's supposed to go to minus infinity. If you want to have a confined piece of fault that fails, you use one at the top that slips the amount you want here, and then you put another one coplanar below that slips the opposite direction. And so you get a kind of a confined patch of slip. And so that's what this shows. This is the top of one dislocation that would go to minus infinity. This is the top of the second dislocation, also going to minus infinity, with a negative B, which is just the slip. And so down here, B and minus B are counteracting each other, so there's no effect from this part. And we only have this finite source of deformation from here to there, this length lambda. So, and we can, in the case of the dip slip, we calculate the horizontal and the vertical displacements. So here's the main equations that we would use, so we can go back through that. But let's just do Bora Peak first. So here is the model for Bora Peak. So we have one dislocation that would go down to minus infinity, and we need to get rid of the effect of its lower portion. So we put a second dislocation on here that has reverse slip from minus 13 to minus infinity. And so that counteracts the normal slip from this guy down there. So that just gives us this finite piece of fault. And if you look at this displacements that I calculate, it's quite similar to what Bora Peak example was. And so we can do the same. So that's like here, they tried it with the district fault, it doesn't work. But when we do it with a straight fault, it works pretty well. So that, compare that with this figure right here. So my arrows that I just calculated would make that line right there. So then the second example would be the Loma Prieta case, so blind fault. So here I have the top of the fault kind of, if you compare this model with these ideas like this one, this is a 3D, oh thanks, 3D view of this here would be more complicated view of my model, but that locked part up there that didn't break would be here. So that's trying to simulate this. Okay? So the last thing that this teaches us is, and this is not now my calculation, this is in the textbook by Stein and Weiss-Session, so it's a geophysics textbook. They show the same thing. So you can use the same type of dip slip, and if it's a vertical fault, you have kind of symmetric displacements, and you see the depth goes down to about 15 kilometers, and if you go out about 15 kilometers, you kind of get about half of the displacement. So that's what I mean by this rule of thumb. It's just a basic idea or intuition that the depth of the source scales with the wavelength of the deformation. So then you can have this inclined case. So this would be like kind of like the subduction case, where remember in our little cartoon we saw this patch slip, and it pulls the, it pulls that GPS receiver back, but it also lifts the seafloor right there. So that's your tsunami-genic displacement right there. Now, here's what happens. You can also have the blind fault, so you can push this down deeper, and you see the effect. It kind of mutes the signal, and that's again an indicator of the depth to the source. So what I've been saying is this kind of size of the source and the depth of the source influences the sharpness of the displacement at the surface. And that's something just you should take away always. Anytime anyone shows you GPS data, GPS velocity, you want to say, okay, do I see any discontinuities? Is it, some deep slip, or is it co-seismic, shallow? What can I infer about the geometry of the fault based on this exploration? So here's just the same kind of calculation now, one that I made. So here's a vertical one, and all I do is I pull the bottom down. So here's the displacements for 1 meter of slip with just the shallow. I go to 510. So you see the maximum displacement stays the same, but the width of the displacement increases as I pull the depth down. Here's the changing dip. So this is that subduction case, but tipped on its side. 10 would be this one. So that's like a subduction example. And then here is the buried source. So if you push it down at 5 kilometers deep, actually the peak displacements are away from the fault about 5 kilometers. So again, that depth sensitivity is there. So that's my dip slip story for you guys. So let me just show you, and then I'll go around and help everyone. But what you want to do is you should be able to just do, I don't know how many people know MATLAB, at least a little bit. Okay, not just a little bit. Okay, so it's just a programming environment. So it kind of lets you do a lot of math pretty easily, but also has integrated graphics. And so it has, I'll help you get started, but this is called a script. So it just does all these commands. And all you have to do is just change, you can change these pieces up in here, but go slowly. And then don't change anything below here. And if I put this percent at the beginning, it's like a comment. So just everything above that is what you would change. So it has the dip is 135. So you can experiment with these. You just change them. Has the B, this is the slip. So 2.5 meters of slip. Okay, Berger's vector is just that term that comes from the mineralogists. Xi upper and zeta upper, these are the where the top of the fault is. And these are in meters. Everything's in meters. So this is the X position is at 0, and then the top is just 1 meter below the surface. Because sometimes if you make it exactly at 0, there's a divide by 0 case. So we need this to be close, but not exactly at the surface. And then you see down dip length is 18,000. So this is 18,000 meters down. And then the X max, X min, this is the width of the study. No, just the width of the calculation. The locking would be this 18. But this is for a dip slip case. So this is the, remember this more complicated looking equation in here. This is using this math right here. The Z is just the depth to the tip. So in this case, it would, the Z is just how far down it is to here, and X is where this point is. So XZ is the coordinate of the tip of the fault. And then this lambda is just the length of the fault. So in this case, in MATLAB, it's 18,000 right here. It's 18,000. So that's the length down. Then X max is 15,000. That would be how far we go to calculate this direction. And then minus whatever 20,000 is how far this way to calculate. And then you can see in the MATLAB, this 1,000 is just every kilometer I calculate. Okay? So then all the math is down here, and it's just doing this addition. Sort of, it takes the upper dislocation and it takes the lower one, and it just adds them. But the lower one, you see, I'll just show you one. So there's upper and lower, and you see right here, I put in the negative components of slip. So when we add it together, these negatives counteract those lower parts of the fault along the dislocation. So anyway, you don't have to worry about that part. If you just push this arrow, it should work. So you can experiment. So what this shows is actually, let's just try here. So this shows the fault, same on both sides. And then this is the X displacement. So this is, in this case, you see negative is going to the left and positive goes to the right. So it makes sense because it's a normal fault. So the left side goes down, right side goes up, right? Or it goes like this. And this is the effect of the upper dislocation. That's the effect of the lower dislocation. So it's this plus that equals this. And then here's the verticals. So upper dislocation, lower dislocation. This is that signal that looks like the Bora peak case that I was showing. So these are we say the components, but if you use the arrows, this shows you the, both components together. So there's the fault would be right here, and it's going down like this. And so just compare this displacement with the Bora peak case. So that's just right there. That is the same as this. Okay, so now let's change something simple. So what you would do is, let's say, well, one if it was going to be shallower. So I made it 10 kilometers deep. So then you just push this. So you can see the change. It got a little tighter. Okay, so now let's try, because I know you guys we have our, so let's do 20. Let's keep it deeper. Okay, so now what let's do is, so here's a trick, is it's dipping like, it goes 135. So if you think of dip, it starts here at 0, 90. So it's over here. Dip is 135, right? So let's try what happens if we do dip as 45. So it should change the dip, but it might change it into a reverse fault. Okay, so it's going around. So let's just look. We can tell by inspection. Yeah. So there's a 45-degree reverse fault, and you can see the, you kind of have to go between the two, what they're doing. So let's slowly build the subduction zone case. So let's make it shallow. So what do you guys like, 25 degrees for a subduction interface? So here's a reverse fault. So you really see that displacement near the fault. But now let's try to make it a little bit blind. So here remember these are in, this is the upper tip in meters. So the tip is at 0. So let's just look at this again on here. So you see the top of the fault is there at 0. It goes to there. But let's say we know for a subduction zone that usually this lock part's not coming all the way to the surface, although it did in Japan, but a lot of times it's blind. So we can put the tip of the fault down 1,000 meters. Yeah, so here you can see, a little bit hard to see because of the scale, but you see it's down. So it makes it a little bit smoother. So if we go back, let's go make this 1 again. So don't put 0, as I said. If you make it 0, it divides by 0, so it's bad. But 1 meter below the surface is the same as at the surface. So it's very sharp. So the power of the MATLAB is you can, if you do this right, kind of get these guys to sit in here like this, and then you can rearrange your windows. Whoops. I lost it. So if I put this guy down here, so you do your windows so they're all arranged like this, there, and then get this thing a little bit lower here. So now we can kind of have our little calculation engine. So I have 1, so let's change this to 1,000. So it went a little bit deeper, starting, basically it's still, it's kind of hard to see the effect there. What it did was it pulled the tip. Yeah, so it basically rounded the edge off here. So let's try it if we go to 10,000. So if we make it really deep. So there, all you see is the uplift. So see, that's the blind. That would be if you have a deep thrust earthquake. You just lift a very smooth way. So let's try like 5,000. So maybe 2,000. Yeah. So somewhere around between 2 and 5,000, we start to get this pretty good sensitivity to the tip position.